In the 1960s, computing power occupied entire rooms, defined by rows of red IBM mainframes and massive spinning tape reels. Because these machines were so scarce, connecting to them remotely was a massive logistical and financial challenge. All communication ran through the telephone grid, a system built on circuit switching. To make a connection, the network had to lock open a dedicated physical copper path between 2 points for the entire duration of the exchange. This worked for continuous human speech, but computers process data in sudden bursts. On a circuit-switched line, researchers were forced to pay for a dedicated long-distance connection even during the long pauses between data transmissions, essentially buying hours of silence. This physical telecommunications monopoly was the structural bottleneck that made digital communication financially impossible for anyone outside of major government agencies. In 1965, British mathematician Donald Davies recognized this inefficiency. He proposed a decentralized architecture that prioritized information flow over physical line ownership. Davies' solution was to slice digital messages into tiny, uniform chunks he called packets. These would be thrown onto the network independently, mix with other data on a shared wire, and reassemble automatically at the destination. When the British government declined to fund a national rollout, Davies' team shared the concept with American researchers. With Pentagon funding, they used packet switching to build ARPANET, the precursor to the modern internet. This shift established the conceptual foundation for the layered protocol stack we use today. To understand how the modern web functions, we have to trace a packet's travel diary as it ascends from raw physical energy toward high-level code. Every digital journey begins at layer 1, the physical layer. Down here, data is simply raw energy, electrical voltages on copper, photons pulsing through fiber optics, or radio frequencies in the air. To navigate its immediate local environment, like moving from a laptop to a router, the packet enters layer 2, the data link layer. It uses a MAC address, a hardware identifier burned into the network interface card, to find the next physical hop. These two layers bridge the gap between digital concepts and physical reality. When a system fails to connect at all, the problem almost always originates in this hardware wilderness. At layer 3, the network layer, the packet is assigned an IP address, a global coordinate for routing. We've exhausted the 4 billion addresses of the original IPv4 standard. Modern infrastructure relies on IPv6, providing enough unique combinations to label every device on Earth. Packets rarely travel in a straight line. Instead, they hop across dozens of intermediate routers, each consulting a routing table to decide the best path toward the final destination. This hop-by-hop logic provides the network with its resilience. If a specific node fails, Layer 3 allows the packet to find a detour, ensuring data continues to flow even when portions of the physical infrastructure are down. At Layer 4, the transport layer, the packet identifies its target application using a numbered port. For absolute accuracy, TCP performs a 3-way handshake: SYN, SYN-ACK, and ACK. This ensures every packet arrives in order and without corruption. Other applications use UDP, which skips the handshake entirely. UDP prioritizes speed over reliability, which is why it is used for live video streams and online gaming, where a slightly glitched frame is better than a long delay. Layer 4 is where developers choose their fundamental trade-off: the guaranteed integrity of TCP or the raw velocity of UDP. At Layer 6, the presentation layer, the packet undergoes security customs. Using TLS encryption, the system verifies the server's identity and decodes the secure contents into a format the application can understand. Finally, the packet reaches Layer 7, the application layer. This is where protocols like HTTP and WebSockets live, turning the raw payload back into usable code. The packet is stripped of its routing headers and sequence numbers, handing the final data directly to a web browser or a Node.js server as multimedia or text. This complex journey is what allows us to translate the simple movement of energy back into meaningful human communication. This entire process, from a transatlantic fiber cable to a loaded response on your screen, typically happens in roughly 50 milliseconds. When a distributed system breaks, understanding this map allows a developer to reason from first principles. They can determine if a timeout is a Layer 3 routing failure, a Layer 4 connection exhaustion, or a Layer 7 misconfiguration. This brings us back to Donald Davies. While he was largely sidelined by the history of ARPANET, Every packet sent today follows the logic he sketched in 1965 to stop paying for silence on telephone lines. Billions of travelers follow his map every second. Meanwhile, the original architect is remembered by a single plaque behind a security checkpoint in Teddington, a quiet reminder of the man who defined how the world